Thanks, Alexi, and thanks everyone for being here. Thanks, Audrey, for being here. If I am misrepresenting anything, please feel free to jump in and add any clarifications. So today's topic is about TAOBench. And before I go into what TAOBench is, let me start with the problem statement and the motivation here. So with the large number of social network applications, the scale of data and the query volumes that we have been seeing is exploding. And this is challenging the limits of some of the existing data stores used in many of these social network companies and scenarios. But at the same time, there is a lack of publicly available and realistic workloads that can accurately simulate these kind of social network workloads. And you may be asking, okay, why do we need such realistic workloads in this case? The two main categories or buckets that the paper calls out. One is, hey, without this, how can we really understand the limits of the existing data stores and systems? And if we don't understand the limits, how can we work on research to go and improve those systems, right? Like how can we build the appropriate mechanisms to overcome those limitations? That is one category. And then in the industry, as teams and services use these data stores and continue to come up with new use cases, new features, new customer requirements, how can you really evaluate those new features and new workloads in a very early fashion, right? Like how can you know about problems with new scenarios, evaluate it in a very with very short feedback loops without having to find out about those problems like just very close to production and kind of delay your rollouts and all of that, but you really want to get a very, very short feedback loop to iterate and move quick on, hey, I'm trying to introduce this new workload. How is it going to look like? What kind of performance or concurrency problems I'm going to hit with it? So that is another motivation. And this is the reason TAOBench, which is an end-to-end open source benchmark for social network workloads, has been made available to meet these two goals. So, but don't such benchmarks exist already? Well, yes and no. There are many benchmarks for other types of workloads, all the OLTP workloads, which are doing a good job in that space. But social network workloads are special and different. They are very, very read heavy. And I think the TAO data shows more than 99%. I think around 99.7% is basically reads. And many of these there are a couple of social network specific benchmarks that the paper calls out, existing ones, but they have one or more of these problems, right? For example, some of them are derived from synthetic data, and that's not really going to give a very good it's not going to match what you're going to see in production, so it kind of defeats the purpose of a good benchmark. And then some of them don't support, say, transactions, and transactions are becoming more and more applicable in many scenarios, even with social network style workloads. I'll go into some of those examples later in the deck. And then support for expressing, say, hey, I want, due to this compliance reasons, I want these two to be co-located on the same shard, or for some privacy constraints, etc. So the benchmark ideally should be able to express all of these, including like these kind of support for transactions, co-locations, preferences, and then preconditions, right? You may want to do some optimistic concurrency control and say, hey, I want to read an object, I want to do some business logic on it, and then I want to write it back, but on the condition that nothing else has changed that particular key in the system. So that kind of a precondition you want to be able to achieve even with a benchmark. And TAOBench takes all these properties, desired properties, into consideration. It's an open source benchmark, which is derived based on production data from TAO, which is the social graph data store at Meta. And it has also been validated that it actually accurately matches the patterns you would get with production workloads. So what does the paper cover? The paper covers a whole bunch of things. The desired properties, as I was mentioning, for the benchmark, what an ideal benchmark should cover. It also provides a brief overview of TAO, which is the social graph data store at Meta. Sorry about the background noise in case you're hearing it. I think there is some lawn mowing going on outside my home. Is that distracting? Then I can try to move to a different room.
I think it's fine. We don't hear anything.
Okay, great. So the paper also looks at the production workloads from Meta, like using the on the TAO data store, and comes up with many observations in terms of, hey, here are the access patterns we are seeing on the social graph, and use that to distill a set of key parameters. Like here are a set of, we think these are like the 10 parameters, or 10 is an example, but here are the short set of distilled parameters that we need to be able to express in a workload configuration, and talks about what the benchmark API looks like, what the architecture of the benchmark system is, and importantly, how it can be extended using an adapter layer to be able to go and validate any kind of distributed database for these kind of workloads. And it also talks about how the impact of this framework at Meta itself in terms of what the benefits have been so far, and also I think I already covered the extensibility part, how to use it to validate other distributed databases. So the 5 crucial properties called out by the paper on what an ideal social network benchmark system should cover. Number one, ideally, it should emulate social network requests as realistic to the production environment, as close to the production environment as possible, right? And the way TAOBench achieves it is it derives these workloads based on observing the real world production workloads on Facebook's own social graph system, which is TAO. And then it's ideally the benchmarking framework should allow you to express transactional requirements. And TAO itself was originally built as an eventually consistent system, which is Facebook's social graph data store. But over the years, they have added support for expressing more consistency, right, in terms of to make the lives of developers using the system simpler. It supports now things like multi-write, where you can say, hey, I want these two or these n number of operations. I want it to be part of a transaction, and that could be either single shard or across multiple shards. They also support read your own writes consistency, atomic reads, etc. I'll try to cover some of that later. But you should be able to, a system should enable you to benchmark workloads should ideally be able to express such request patterns. That's the main takeaway from number 2 here. And the third point, I briefly touched upon it in the introduction, where you want to be able to express co-location preferences for various reasons. So sharding is not just an implementation detail, but you want to be able to say, for compliance reasons, privacy constraints, any kind of scenario where the user intent is, hey, I want these two things to be co-located on the same backend shard, you want to be able to express that. And the reason behind that is that can have an impact on the performance of the system, and you want to be able to use the benchmark to find those kind of performance issues. So that is number 3 here. And number 4 is about, hey, I have different types of query types, and like there are so many applications built on top of these kind of distributed data stores, and you have varying application workloads, and they change very dynamically. So you want to be able to model all of that without being too prescriptive about what those query types are. But ideally, you want the benchmark to use some kind of probability distributions to kind of generate those workloads without being too hard-coded to specific query types. So that is the 4th property identified by the paper. And the 5th, the last but not the least, which is about multi-tenant behavior. The way, for example, TAO is used is there are many product groups using TAO as the social graph to access the social graph at Meta. And in addition, there are also mechanisms like other infrastructure built on top of it. So it's kind of like an infra on infra model. But in all these cases, there is basically you can think of multiple tenants which can potentially access the same data, and hence one application's behavior can affect another product group depending on that same data. And you want the benchmark tool to be able to help you model this so that you can actually find such issues in production. So I'll pause here for any questions so far before I continue. Okay, so and please feel free to interrupt anytime for any questions. So a background on TAO itself. So TAO is Meta's social graph data store. It's heavily optimized for reads because of the nature of social network workloads. It's a geographically distributed in-memory data store. It's heavily sharded for like scale out, like horizontal scale out. And it also has a tiered architecture, like multiple layers of caches, and then there is an underlying MySQL database backing the actual data. So 10 billion plus reads per second, 10 million plus writes per second. So you can see it's very read heavy. So I think this maps to 1 quadrillion requests per day. And the data model itself is very, very simple. So you can have, since it's a graph, it's modeling graph data. So you have objects, which are kind of representing nodes, and associations or ASOCs, which are the edges. So I have an example here, which I got from Aaron's talk on YouTube. So for example, here, if you have something like this, say, like there is a check-in post, right? Alice checks in at the Golden Gate Bridge and tags Bob. And then this is like a you can think of this as, hey, there is a graph node here is Alice user ID, like, I mean, the node type is user, there's a specific user ID, name, Alice, etc. And then let's say Kathy replies to that saying, wish we were there, and David likes this, right? So that can be modeled using this kind of a graph, where you can see, I have these nodes with ID, type, data, some data, and then there is this edges, which are the associations between the objects, which have some metadata about what it is, right? So, and it could also have some additional data. For example, here, I think this edge has a time part of it. So this is the objects and the associations. And here, the API itself is intentionally has been kept very simple, like basically with the principle of do a few things, like, but really well, so that it can work well at scale. So you can think of API being like, hey, I have like point get, I want to go get a particular object or an edge. And then there are some range and count queries for, like, say, hey, I want to find out how many friends a particular user has. That would be like one of these queries. And then there are operations to like the write operations, right? To insert a new object or an edge, insert, update, delete objects. And then originally it was built as an eventually consistent system, and then later on evolved to also support some kind of a multi-write transactions. For example, if I want to say I want this object and that edge to be written atomically, I could use a write transaction for it. So I think I covered some of these. So I think the three examples of what kind of consistency you can get additionally. Again, this is like an optional additional thing, right? Like bulk of the writes are still like the without the transaction, but now certain use cases may require this kind of transactional semantics for better consistency. So they could use this. I think just a very short summary, like one is the single shard, multi-shard transactions that I talked about. And then there is the read your write consistency. For example, I think the example from Aaron's talk is if, say, this comment was posted by Kathy, and let's say this object write succeeds, but the edge write fails, then you would end up seeing an inconsistent state here, right? So that is the first example. And the second one is more like if Kathy writes this and when she reads back, she should be able to see the thing even if she's hitting a different web server, for example. So that's the read or write consistency. And the last one is the atomically visible read transactions. Again, I think there's another paper. I didn't get a chance to go into that. I think that's also from Audrey, I believe, Ramp Tau, which talks about how to get transactional reads. So again, this is just a background on Tau itself. And coming back to TAOBench, now we talked about those desired properties, right? Like the 5 properties. Now, how do you really achieve those 5 goals, right? How do you get this? Hey, I want to accurately emulate social network requests. I think this is the most important one. So for this, the paper talks about how the team characterized the workload, Meta's workload running on Tau. So they analyzed the traces of requests over 3 days. So you get a broader distribution of what's happening over 3 days, and then downsample that data uniformly to record every request. So basically not just do it randomly, but you like use the, like if some request happened on some particular object ID, you want to get all those some kind of a consistent sampling, right? So you want to get all the requests on that object. Similarly, for an edge, you want to get all those requests which happened on it. So that's based on like a hash on this object ID or the association ID that helps you find things like, hey, where is the contention happening for what kind of objects or what kind of edges, etc. And then they categorized into 3 groups of operations: reads, writes, and write transactions. And you can see that reads constitute like a really big portion of the overall observed workload. And again, all this info was based on some aggregated data, so there is no privacy risk here or privacy implications here. And then the analysis was limited to the top 400,000 keys due to some reasons. So this helped the team study the features of the request patterns to Tau. And there are a lot of examples in the paper, and I'll just cover 2 here in the interest of time. I think one of them is, hey, the read and write hotspots do not always align. So I think one of the examples here, if you see here, the graph x-axis is the reads per day and the y-axis is the writes per day. And you see these 2 different things here. So let me give you an example. So let's say a celebrity posts some kind of a picture and there are a lot of views on it, and then probably a large number of likes on it. So this is basically the like association access distribution across the top 400,000 write keys. So there you will have a large number of reads and a large number of writes, right? That example of the celebrity posting a picture or something. So that is this example. Whereas there could be other internal applications using Tau, and they could be like, say, some kind of internal data migration or similar systems that are also doing a large number of writes on some keys, but they don't get read as frequently. So the reads are fairly low, but you can still see the writes are really high here. So this is kind of an observation based on that data gathered from the production data. So this is one example. Another example or another pattern that is talked about in the paper is the latency distributions of different operation types. So here you have reads, writes, and write transactions. And you can see that there is a bimodal distribution here for each of these. And that's mainly because of things like cache misses, right? So, and writes and write transactions are the average. I think this models the average latency, and the average latency is higher because it involves like a cross-region request. For example, if I write a key and the primary database for it is in a different region, now that write has to go there. So the writes can take longer. But I think the interesting things here are the benchmark needs to really understand all these so that it can actually model all of these appropriately. I think that's where the main takeaway of many of these access patterns explained in the paper are. And also the other implications are things like, hey, it looks like the cache is working very well, like the different layers of caches, etc. But I think there is also the potential for things like the metastable failures, right? In terms of this kind of a bimodal behavior. The paper doesn't touch much on it, but I think that was one potential question on, hey, what are the implications of this kind of a bimodal distribution, and does it really are those other mitigations in place for preventing those kind of metastable failures when, for example, like some layers of caches are unavailable? But that's kind of orthogonal to the main TAOBench paper. So using, and there are many more of these, which I'm not currently covering. But the main summary is, like, based on all these things, the team was able to say, hey, we can take this, we can distill all of these learnings, and we feel that, hey, here is a small set of parameters which can be used to characterize the workload and to be able to serve as our building blocks for the benchmark itself. So you can see things like what should be the size of a transaction, the sharding information, things like that, like request sizes and all of that. And there is actually two categorizations here. Some of these are general enough to be able to map to any data store, not TAO specific. And there may be some which are TAO specific. Like, for example, like the read tiers, right? So TAO itself has like a multiple tiers, like there is a request can be served from a client-side cache, or from TAO's cache itself, or from the SQL, MySQL DB if it's not in the cache. So you can actually tell the workload configuration can say, hey, I want 85% of my requests to come from the cache and not from the DB, right? So all those might be TAO specific. But overall idea is, hey, there are these parameters that can be used to model the workload configuration. So how do we go from those parameters to actually building the benchmark? So TAOBench also has an API, right? So you have all these workload configs, but ultimately you want to have an API that expresses what requests you're going to be able to send to the system that you're actually validating. So it actually models after the TAO API, and it's a very simple API. So there is basically, hey, I want to read a key, which is like a regular read API. And then there is also, I want to read a group of records atomically. Like I want that atomically visible read, like either my read should see either all the effects of a transaction or none, right? So I want to do that. So that is basically the read APIs. And then write, I want to write a key with some preconditions. For example, this could be used for, like, say, the optimistic concurrency control, right? Like the example I gave in the beginning, which is, hey, I want to read something, do some business logic, and then write back that key, but only on the condition that that key hasn't been changed from the time I read it. So that would be a write with preconditions. And then here, this is basically a write transaction. I want to write a group of records, and these could be on either the same shard or multiple shards, but again with a set of preconditions. So this is the TAOBench API, and I think it doesn't currently cover the range and count APIs, which are in TAO, but I think that's planned for the future. But the main architecture is it has a scalable distributed architecture. The core of this is this driver. So you have these workload configurations, and there are 3 workload configurations that have been open sourced. That's based on Meta's workloads. And this expresses all these, like the parameters we saw, the probability distributions for those. And then the driver can load this config, and it has 2 phases. One is like a preparation phase, where it can go create some initial data, right? It has to go and say, hey, here are like a bunch of objects I'm creating. And maybe it will do some operations to warm up the caches. Maybe it will do some reads just to make sure based on the desired the weights for the different tiers, it will warm up some caches, etc. And then the phase 2 is the actual execution phase. There'll be different client threads and where it will actually go and generate those requests. And there is an adapter layer. So this is not specific to Tau. There are actually 6 or 7 adapters already written for different other systems. And I think that's the extensibility mechanism. You could go write your own adapter to leverage this with a completely new system. And given that this API is fairly simple, it should be translatable to whatever API your data store supports. So the paper talks about some of the interesting considerations in the preparation phase. For example, you want to have enough number of objects and not have a really small initial population so that you don't get into some artificial contention between keys, etc. So have a big enough pool to avoid contention and all of that. And then I'll show you the config itself, right? This workload config. So it contains the probability distributions for required workload parameters. We saw these parameters earlier. And then there are 3 open source workload configurations. This workload O is the overall workload, which is like very read heavy. Again, this is based on the real data from the Tau patterns itself. And then there is a transactional workload. And then there is like a speculative workload, which is basically the workload A, which is things which are not transactional right now, but could become transactional in the future. So it's kind of a new workload. So this is an example configuration file that I got from the GitHub repo, corresponding GitHub repo. So it talks about all these parameters. And interestingly, it also has things like errors, like to simulate different kind of errors, transaction errors, and all of that. For example, you can see read tiers. I want 1485.1, like distribution of 85% of my requests should be served from the Tau cache, 1% should go to the DB, 14% from the client cache, if I'm interpreting this correctly. So, any questions so far before I continue? Cool, I'll continue with this one. So the validation approach is, hey, like, do the request patterns generated by the benchmark, are they in line with those from production, right? That's the, to validate that first property or the first goal, is the benchmark accurately representing or capturing the real social network production workload. So for this, the paper talks about how they looked at request latencies and contention rates. The request patterns generated by the benchmark, hey, do they have the same request latencies, same contention rates from what we are seeing in production? So the implementation approach is there is a C++ adapter to send requests to Tau. Each thread that we saw here acts as an individual Tau client. Each of these client threads. And that mimics how Tau is used in Meta. And then there is a separate Tau deployment with its own cache and DB, and where the requests are sent to. And cross-region performance, like for the write, if you remember, the writes actually go to the primary, the instance, which is the primary region for that key. So to simulate that, some network latency is also injected. And the validation was done using 2 transactional workloads, referred to as T.1 and T.2. And one of them updates an existing object, and I think it adds a new edge, new association. And the other T2, it covers multiple, a transaction that updates keys across multiple shards. And here are the results of the validation that the paper calls out, which is for both these workloads, right? So the first one is for T1, workload T1. Second one is for workload T2. And this one, I'm just showing only the request latency, not the contention rate. The paper talks about how the contention rates are also very similar between prod and benchmark. But if you look at the request latency here, you can see that the request latency distribution between the benchmark and production are very, very similar. And same with the other workload. So this kind of validates that, hey, this benchmark is actually accurately modeling like a production workload for social network workloads. The paper then talks about use cases of TAOBench at Meta. So there are 4 main things talked about. I'll cover 3 here. So one application team at Meta, they wanted to add a new transactional use case. And normally what they would have done is, without TAOBench, they would have had to just introduce it and then in some kind of pre-production environment, test it, and then figure out some problems and then delay the rollout, figure out how to fix it, etc. But with TAOBench, they can get an early end-to-end testing or validation, like to shorten the feedback loop. So what they did is, with the TAOBench, they were able to evaluate that new transactional workload, referred to as T.3 here in this table from the paper. And what they noticed is this log conflicts compared to another workload called T.1, the previous one we looked at. There was like a 26% increase in the log conflicts, even though the latency itself was lower than the previous workload, the log conflicts increased. So they were able to identify that problem early, and they were also able to confirm that they were seeing the same thing in production. So just proving that TAOBench was able to identify that exact same problem much earlier on, helping teams to iterate faster and not like have a really shorter feedback loop. So that is one use case. The second use case is teams at Meta wanted to understand what would happen if certain logs were held for extended periods of time. I think, again, this goes back to write transactions which are implemented using like a 2-phase locking and 2-phase commit mechanism, particularly for the cross-shard transactions. And what if there is a network delay and you have to hold a lock for much longer? So this shows the, with TAOBench, you can just model this and find out what will happen in that scenario, right? So here you can see that with additional lock hold time, right? So here, as the time increases, how much milliseconds you're holding the lock for, the error rate, the contention increases, because now somebody is holding on to that lock for more time. So other transactions are probably seeing more contention, and then obviously you want the transaction to time out sooner so that you don't hold up those resources for so long. So you start seeing these timeouts. And then 3 seconds, I can pretty much, I think it just times out. Like you see way more of these. So this is again a way to understand the reliability of the system, understand how resilient your system is to some conditions, like, hey, I have a network delay for 200 milliseconds, what's going to happen? You can teams use TAOBench to understand such system behavior. And then the third example, or the use case at Meta with TAOBench, talks about the need for new APIs, right? So I previously mentioned about this optimistic concurrency control and the precondition, where let's say you read a key, do some business logic on it, and you want to write back on the precondition that the object isn't changed by somebody else. So the longer you take between the initial read and the preconditioned write, the more the probability increases that the preconditioned write is going to fail, because that object could have been modified by somebody else. So here you can see again, as the average wait time between the initial read and the precondition write, as it increases, the error rate goes up, right? For example, here between 30 milliseconds and 150, I think the paper talks about how it actually doubles. And this can happen with cross-region writes, right? If your write has to go hit the primary of that key is in a different region. Now, due to network delays, realistically, you might encounter more error rates. So this analysis helps teams identify and say, hey, maybe we should have a new API that can help us do the write in the primary region itself to avoid holding on, to avoid this wait time being between the initial read and the write being much longer. So there is a, for example, I think the paper talks about there is an update counter API where the read and then the subsequent write also finish in the same primary region. But I'm not 100% sure if that new API was added based on this analysis or was it already existent. But the overall idea is TAOBench can help you identify such scenarios. And then this one I will not go too much into detail, but this is another use case used to evaluate high fan-out transactions. So the part I haven't covered is how TAOBench was used to also test 5 other distributed databases. I think it talks about PlanetScale, TiDB, Cloud Spanner, and 2 more other distributed databases. By using this adapter layer, you can write your own custom adapter. So there are already those 5 or 6 adapters. And there were a bunch of issues or things that were observed. For example, I think there is a paper from like a blog post from PlanetScale on how they work with the TAOBench team and observed certain issues happening based on this benchmark and how they fixed it in PlanetScale. So I ran out of time to go too much into detail on that part. But since Audrey is here, maybe we can get Audrey's thoughts on that as well. That was pretty much my prepared content. Any questions, any comments?